Next, we will study the mass flow inlet boundary condition. Mass flow inlets can also be used with incompressible or compressible flows. Here we have to specify the total mass flow rate, which is given here. We can specify total mass flow rate or mass flux, and same reference frame and flow direction options are required as in case of relative reference, as in case of velocity inlet, which is the direction, in order to specify the velocity as well as the reference frame selection. We have to specify other scalars such as total temperature, turbulence, species, etc. in separate tabs, which are here. We can also use this boundary condition as an outlet by selecting outward normal as the direction specification method. Till now we have seen flow direction specifications, but how do we determine the flow magnitude knowing the mass flow rate and flow direction in case of mass flow inlet boundary conditions? For that, we have to use the velocity definition and mass flow rate definition or values in order to calculate the velocity directions. So if we know the mass flow rate, we know the area, that is a boundary face area, and we can calculate the normal velocity and tangential velocity components using those. So by definition, this is the normal velocity component, which is mass flow rate divided by the area. So this will be the normal component and this will be the tangential component. For relative reference frame formulation, we substitute the relative velocity and direction for absolute velocity. Next boundary condition that we will study is the pressure outlet. Here we have to specify the static pressure at the outlet, which can be a constant or profile. We can employ a simple radial equilibrium assumption which computes a radial pressure variation. The specified pressure is then assumed to be the hub static pressure. The specified pressure is then assumed to be the hub static pressure, and this particular boundary condition of outlet is appropriate for axial compressors and turbines where the flow is parallel to the rotational axis. We must also specify backflow variables like total temperature, species, phase, mass fraction. Other options that are available is target mass flow rate, non-reflecting boundary conditions. We refer to a term called as backflow, which is the reverse flow at the outlet boundary condition. This typically occurs when the static pressure in a cell adjacent to the pressure boundary forces the flow in direction opposite to what is to be intended by the physics. For a pressure inlet where the boundary pressure is less than the P cell, that is PB is less than PC, boundary total pressure is assumed to be static pressure for the purpose of determining the flow velocity. Backflow scalars are obtained from the solution in this particular case for a pressure outlet condition where the boundary pressure is greater than the cell pressure. In this case, boundary static pressure is assumed to be total pressure for the purpose of determining the flow velocity, and backflow scalars like temperature and species are required to be specified when in case of pressure outlet boundary condition. In case of reverse flow, for moving reference frame problems, the reverse flow direction is relative to boundary in the absolute frame if absolute velocity formulation is used, and it is relative to the boundary in the relative frame if the relative velocity formulation is used. Next boundary condition that we will study is the wall boundary condition. If moving reference frame is used for fluid zone, a stationary wall means stationary with respect to the moving zone. This is the recommended specification of wall boundary condition for all moving reference frame problems. We have to set the rotation axis and the origin same as the fluid zone for stationary walls as well. In the absolute frame, we use 0 rotational speed. Stationary surfaces have 0 rotational speed. For moving surface, we use 0 rotational speed related to the adjacent cell zone. So this 0 rotational speed of stationary surfaces is in absolute frame, and for moving surfaces, 0 rotational speed is related to the moving reference frame. This means the moving surfaces are actually moving with the moving reference frame velocity. Now, which sort of physics models we can use the single reference frame model along with those? Which sort of models is it compatible with? The moving reference frame is compatible with most of the physical models in Fluent, including the turbulence models like the turbulence RANS equation based models, LES model, It is also compatible with the heat transfer, conduction and convection type of models. It is also compatible with multi-phase, DPM models, mixture and Eulerian model, including the cavitation model. So you can use this particular single reference frame model with a lot of other physics models as well. And material properties, we can use it with the ideal and real gas model, and temperature dependent properties are also compatible with the single reference frame model. So after setting up the single reference frame model settings and boundary conditions, the next particular settings are with respect to the turbulence model that we are going to use. So wide range of turbulence models are compatible with the moving reference frame model. When we use LES, we use it for unsteady flows where high resolution is important, like acoustics, combustion. We use RANS based model for good accuracy in case of the RANS based models which are there, like the K epsilon, K omega, the K omega SST, and the Reynolds stress model. Those are actually those can provide good accuracy for most of the steady state and unsteady state problem as well. And this particular model works best with structured grid which resolve the boundary layer on wall surfaces. So when we use turbulence model along with the combination of moving reference frame model, we have to consider a boundary layer resolution on the wall surfaces. In order to get better accuracy, we have to use structured meshes. Now let us see how the pathline modeling or the particle discrete phase model setup works along with the single reference frame model. We can use the DPM and pathline models for SRF problem as well. Particle paths are computed in the relative frame. So if you want to see particle paths in absolute frame, we can select the option in the pathlines graphic user interface. Note that the particles moving in absolute frame may hit the wall surface, since the rotation of the frame is not accounted for. This is a kind of a misleading, or I won't say misleading. This is a kind of a phenomenon that we see because of the selection that we have with respect to the pathline modeling. SRF model setup, the last step in that is of initialization and running the simulation. Good initialization of the solution is often the key to obtaining rapid and robust conversions in case of turbomachinery problem. It is less of an issue for incompressible flows with velocity and mass flow inlets, fixed flow rate problems. In case of problems with favorable pressure gradient and less reverse flow, it is less of an issue. But when we consider complex turbomachinery flow problem, we need good initialization for that. When we use compressible flows with adverse pressure gradient, we have to take care of initialization. A better initialization is required. Now, adverse pressure gradient leads to reverse flow. In case of whenever there is adverse pressure gradient, we have reverse flow and there is simulation instability. There are two ways of providing good initial conditions. In case of single moving reference frame problem, we can use the grid interpolation to patch a coarse mesh solution onto a finer mesh, and we can also use the full multi-grid initialization, which is known as FMG initialization technique. Solution interpolation is the first thing that we will see out of the two. Procedure is to run a coarse grid version of your model, write data for interpolation or the interpolation file, set up fine mesh model, read the interpolation file that you have written, initialize the solution with the interpolation. And advantage of this procedure is it can be applied to nearly any geometry, configuration is easy, but the disadvantage is that it requires a development of a coarse mesh. So you have to do a bit of rework, or I won't say a rework, but a kind of a additional work.